Hi, welcome to the bonus video. I'm just going to be solving a bunch of equations and making sure that we're cool with all the different ways of solving. I'll talk about what's going on behind it. So I want to think about my four methods. And the first one I always want to think about is getting the bases equal. Can I get the bases equal in this one? Yeah, I've got 81. 81, I'm like, okay, is that a 3 to the something? Yeah, it is 3 to the 4th. So please don't crash, thank you. So we get 3x equals 3 to the 4th. So x equals 4. Done. Since these bases are equal, their exponents must also be equal. It's that easy. No problem. Cool. Let's try another one. So again, I first want to think about, can I get these bases equal? In fact, I actually can in this one. It might not look like it right away, but I can. It's going to take a little while, but I can get them to be the same. I'm going to start with that 1/2. I don't like that it's a fraction, so I'm going to turn it into a negative exponent. So I'll make this a 2 to the negative 1. Still got my parentheses, still got my 4y. Then take a look at that 16. That 16 I'm thinking about, now I've got a 2 over there. Can I make this a 2? So let's see, 2 squared is going to be 4. 2 cubed is going to be 8. 2 to the 4th is 16. Cool. Now, I've almost got this cleaned up, but I want to do something over here. I want to use my power rule and multiply those exponents together. So I get negative 4y equals 2 to the 4th. My bases are the same. My exponents must be the same. So negative 4y equals 4. Divide both sides by negative 4. Y equals negative 1. Done. All right, let's try another one. Okay, can I get the bases to be the same? You know, I bet I can, because I've got that 4, and I know that 4 is 2 squared. And I've got that 32, and I know 32 is 2 to the 5th. So let's start with that and then see where we can go from there. So 32, you are 2 to the 5th. That equals that 4. You are 2 squared. You still got your exponent of x plus 1. And then we still have our 2 to the x. Okay, now all the bases match, but I don't have it just a base exponent, base exponent. That left-hand side is a bit of a mess, so I want to clean that up. So I'm going to start with my power rule right here. So this is going to become 2 to the 2x plus 2. Notice how I distributed that 2 into this little binomial that's sitting in my exponent. I still have a 2 to the x, and this still equals 2 to the 5th. Then I'm going to use my product rule of exponents. These two bases match, so I can add these two exponents together. So x plus 2x gets me 3x plus 2. And I still have a base of 2, and this still equals 2 to the 5th. Now my bases match. 2 matches with 2, so this 3x plus 2 equals that 5. So we get 3x plus 2 equals 5. And then this is a good old linear, so two-stepper linear that you've been solving since algebra, so that's 3 divided by 3 minus is 1. X equals 1. And that's done. All right. Once again, my first thought is, can I get these bases equal? 17, can I make you a 5 to the somebody? So 5 to the first is 5. And 5 to the second is 25. In fact, 17 is prime. So I am not going to be able to get these bases to match. So I move to option 2, which is, can I take the natural log of both sides? And I can. So I'm going to ln, ln. So now I have the ln of 5 equals the ln of 17. Oh, 5 to the x. And since I've got an exponent inside of that logarithm, I can bring it in front. And x is no longer stuck up in that exponent. So I'm able to bring it in front, and I'm going to be able to get that x by itself. All I got to do is divide both sides by the ln of 5. So x equals the ln of 17 divided by the ln of 5. And I could leave it like that, but oftentimes I will ask for approximate answers. So I do want to figure that out. Can you not be maximized, please? Now, once again, be careful with these. I warned about being careful when you're typing them in. You want to do the common error that people will do is they'll do the ln of 17 divided by the ln of 5. That's the easy thing to do, and you'll trip right at that finish line. This ln of 5 got shoved inside of this ln of 17 because I didn't close that numerator. So I need to sneak in, so I'm going to go second, insert, so I can sneak in a parentheses there. And so now I'm going to complete that ln of 17. That'll spit out a number, and I'll divide it by the ln of 5. So my actual answer is 1.760. Approximately 1.760. Always round to 3 decimal places, please. All right. Here's another one. Can I get these bases to match? I've got a 4. That's 2 squared. 71. That is an odd number. So there's no way I can get that 71 to be a 2 to the somebody. So I want to take the ln of both sides. Now, before I do that, that -2 is going to get in the way. It's going to make what's inside of my ln kind of gross. So let's just get rid of it. Let's get rid of that -2. Before we take the ln of both sides. So I'm going to add a 2, add a 2. So we get 4 to the 3x plus 2 equals 73. And ooh, maybe that might have changed it. Okay, so 73 is still an odd number, so I won't be able to get it to be some power of 4. So that's just done. I'm not going to be able to get those bases to match. We are stuck. We have to take the ln of both sides. So now I have the ln of 4 to the 3x plus 2 equals the ln of 73. This exponent we can bring in front. I'm going to wrap it up. I want to make sure that all of this 3x plus 2 is being multiplied by the ln of 4 equals the ln of 73. Now I could distribute that ln into that parenthesis, but that's just going to make a mess. So what I'm going to do is I'm just going to divide both sides by the ln of 4 and just get it out of the way. You are in my way, ln of 4, so get out of here. So we get 3x plus 2 equals the ln of 73 over the ln of 4. Now we can continue with that, the ln of 73 divided by the ln of 4, but it is kind of gross, and we're not able to like simplify that thing down a little bit. So what oftentimes people will do, and what I'll recommend that people do, is at this point, that's getting really, really gross. So let's approximate it now. We're going to approximate eventually, but let's very carefully approximate this thing just so it's easier to look at and work with. So let's figure out what this ln of 73 over the ln of 4 is. So ln of 73 divided by the ln of 4. Enter. Okay, so then this is what it is approximately. Now I'm going to be very, very careful about what I type into my calculator, because if I'm careful about it, I can keep my answer very, very exact instead of sticking with this one, and it can continue to domino my rounding errors. So this is approximately 3.09, and I'm just going to do 2 because I'm just using that as a placeholder for right now. Then I want to subtract 2 from that. So subtract 2, subtract 2. So we get 3x is approximately 1.09. And then we divide by 3, divide by 3. So x is approximately, and now is when I'm going to go back to my calculator and be careful with what I did. So it remembers all of these decimal places right now. If I, instead of type all these decimal places, and actually in fancier ones, you can go up to it and hit enter. And so now this is exactly that value. I'm not going to do that because older calculators can't. I'm going to use what I was trained to use is I'm going to press minus and see this ANS. So that's saying answer. So it's taking this exact value. It is not rounding. It's remembering this exact value and subtracting from that. That's what that ANS. You can also get it down here if you press second and then the negative button. So -2. Okay, so now there's that 1.09. And then I can also divide that by 3. So there is my exactish value. It does round closer to the end, but it could mess up some of these later decimal places. Sometimes it does, sometimes it doesn't. Depends upon the problem. But that is a more precise way of getting that exact answer. So x is approximately 3.65. 0.365. I said that wrong, but you can see it on the screen. X is approximately 0.365. Yeah. All right, number 6. Once again, we can't get those bases to be the same. 7 is just not going to mesh very well with 15. Fortunately, there's not other stuff in the way this time, so we'll be able to just very quickly take the ln of both sides. 7, 5x minus 2 equals the ln of 15. Bring this thing in front. So we have 5x minus 2 times the ln of 7 equals the ln of 15. Divide both sides by the ln of 7. And so we get 5x minus 2 equals the ln of 15 divided by the ln of 7. And just for difference's sake, this one would solve exactly the same way as the last one, but I am going to show you what it looks like if we don't approximate and we keep this exact, just so you can see the old-fashioned way I used to do this. Old-fashioned way is I would just keep that, and I would go plus 2, plus 2. So I'd say 5x equals the ln of 15 divided by the ln of 7 plus 2. And then I would divide both sides by 5, making sure I divide the whole side by 5. So x is exactly the ln of 15 divided by the ln of 7 plus 2 all over 5. Now, the reason I stopped doing this is because then I was like, okay, everybody, let's approximate this thing. And you end up typing exactly what I was telling you to do in the previous example. So I would do the ln of 15 divided by the ln of 7. And I would hit enter. I wouldn't try to do all of this at once, because if I did, I'm probably going to make an error. So it's a lot easier to just break it up. There's no reason to just hit a couple extra buttons. In fact, I think this is the faster way to do it. So here's that big gross thingy. Then I want to add 2 to that. All right, plus 2. Great. So this big decimal is the big gross thing that's on top. Then I want to divide that all by 5. Okay, divide by 5. Done. There is my exact answer. And I can see that it's doing things in the order I want them to. The calculator is often too stupid to understand the order of operations and what I'm trying to tell it to do. So it is 0.678 is my approximate answer. All right. Now is our first one with logarithm. So in my first 2 examples, I was thinking, okay, can I get the bases equal? I don't even have exponents, so I can't do that. Do I want to take the ln of both sides? No, because I'll be taking the ln of log 5. Gross. I don't want to do the ln of a log. That's stupid. So then I jump to option 3. Can I change the language? Do I have a single logarithm? Yeah, I only have one logarithm. It is log base 5. Okay, great. So let's translate this thing into an exponential. So this becomes 5 to the negative 2 equals x. And oh my gosh, that just solved it. We do want to simplify our answer. So this is 1 over 5 squared equals x. And it's just 1/25. Cool. That one just kind of solved itself once we translated it. Neat. Easy, easy problem compared to some of the other ones I was doing. Let's try this one. Again, I first think about, can I get the bases equal? I don't have exponents, so no, I can't get the bases equal. Do I want to take the ln of both sides? No, I don't want to do that because I wouldn't take the ln of a log. No, I don't want to do that. That's crazy talk. Can I translate it? Do I have a single logarithm? Yeah, I just have that common log. Cool. So let us translate this thing. That is common log. So common log is base 10 to the exponent of 4 equals 3x plus 200. So 10 to the 4th is 10,000 equals 3x plus 200. Subtract 200 from there, so that's 9,800 equals 3x. Divide by 3. I don't think that divides nicely. So x equals 9,800 divided by 3. It's a big gross fraction, but whatever. But that won't divide? Yeah, that won't divide. So that's it. That's it. These translating ones are actually pretty simple. You might get scared by that logarithm, but just translate it. It solves itself. Let's try this one. Can I get the bases equal? No. There's no exponents, so I don't want that. Do I want to take the ln of both sides? No, I don't want to do the ln of log base 2. That sounds stupid. That's out of the question. Crazy talk. Step 3. Can I translate this thing? Do I have a single logarithm? Yeah, I do. That's log base 2 all by itself. There's no other logs. So let's translate this thing. So that is 2 to the 3rd equals x minus 7. Okay, well, I'm going to actually have to do a little solving here. We get 2 to the 3rd is 8 equals x minus 7. So add the 7, so 15 equals x. Easy peasy. Okay, another example. So get the bases equal. No. I've got logs, so no. Do I want to take the ln? I've got logs. No. Can I translate this thing? Do I have a single logarithm? This time, no. I have 2 logarithms. So it's finally time for our 4th and final method, where are the logs equal to each other? I have log base 7 of something and log base 7 of something else. So even though these two insides are different, they should be the same since the logs are equal. Just like when we got the bases equal, the exponents are equal. If the logs are equal, their insides are equal. So this one's just x equals 2. That's all you got to do. It's done. Boo, boo, boo. Let's try this one. So bases, no, I've got logs. ln of both sides, no, I've got logs. Is there a single logarithm? Heck no, I've got like 3 of the frickin' things. So no. So I want to try to do method 4. I want to try to get the logs equal to each other. I already have a single log base 5 on the left-hand side. On the right-hand side, I've got 2 logarithms. So I want to put those together into a single logarithm. So then I'll have 1 log equals another log. So this, I'm going to leave the same. Log base 5 of x. On the other side, I'm going to write it as 1 big logarithm, log base 5 of, I need to do this multiplied by that. So I've got a FOIL. So that's x squared plus 24x minus 3x minus 24 times 3 is 72. All right. Now that I've got 1 log equaling another log, the logs drop out. Even though they're different, even though that blue one has got so much more junk in it, it is the same as the other one. So we just get x equals this stuff. So that's x squared. I got to combine these two. So that's plus 21x minus 72. Then I got to get this thing equal to 0 because now it's just a quadratic. So I'll subtract an x from both sides. So we get x squared plus 20x minus 72. And we got 0 over here, just like I wanted. Now I need to try to factor that thing. And I have bad news for you, friends. This one is not factorable. If we tried to factor this thing, it's just not going to work out. There's nothing that multiplies to be 72 and subtracts to be 20. So it's time to use the quadratic formula. That's fine. We know how to use the quadratic formula. Don't even worry about it. So we need opposite b, so negative 20 plus or minus the square root of 20 squared minus 4 times our a times our c, negative 72. All over 2a, so 2. So this equals negative 20 plus or minus the square root of 688. I've got my key over there just to make sure I don't mess this up. 688. If I type all of the discriminant into my calculator, discriminant, the thing inside of the square root. 688. If you play around with it on your calculator, you'll find it's divisible by 4. Here, I'll show you. So 688 divided by 16. It's divisible by 16. Cool. So we can break that up into a square root of 16 and a square root of 43. And the square root of 16 is 4. So this one equals negative 20 plus or minus the 4 square roots of 43 over 2. And then we can divide that negative 20 and the 4 by 2. So we get negative 10 plus or minus the 2 square roots of 43. Now we need to be careful with this one. Our final thing about this one is that, remember, we can't put negative numbers into a logarithm. So we need to make sure that this thing turns out negative. So if I do negative 10 minus our 2 square roots of 43, we get negative 23. We can't put that into log base 5. Log base 5 of negative 23 doesn't exist. So that's not going to work, Mr. Minus. How about Ms. Plus? I don't know why I gave those genders to those signs. But we get positive 3. We can put positive 3.1148 into our logarithm. Cool. So let's do that one. But we can't do the negative 23. So x equals negative 10 only plus 2 square roots of 43. If you're giving decimal answer, it was 3.11, and I can't remember the other one, 5. 3.115. Neat. Final example that I got for you in this one, I believe, is, yep, just make sure it was the last one. Same deal. This one's going to work out a little bit easier. We're not going to need the quadratic formula for it, but it's like identical to the last one. But I'll run through the list. Get the bases equal? No, I got logs. Change, take the ln of both sides? No, I got logs. Can I change the language? There's too many logs to do that. Get the logs equal. Okay, cool. I got 2 logs. Let's put them together. I'll put these 2 together. 1 cabin. Log base 4 of x times x squared is x squared minus 2x equals the log base 4 of 2x minus 3. Neat. Now, even though the junk in these 2's trunks is different, since they're both a log base 4, their insides must also be the same. Since those 2 logs are equal, their insides must be equal. So 2x minus 3 equals x squared minus 2x. Okay, it's a quadratic, so let's get it equal to 0. So we get x squared. We can subtract that 2x from the left-hand side, so we get minus 4x. Add the 3, we get plus 3. This one is factorable, so we get x minus 3 and x minus 1. So x could equal 3, and x could equal 1. Now, are these both going to work? I think so they're both positive, so we can put them both in here. Let's see, 3 times 2 is 6, minus 3, that is positive, cool. 2 times 1 is 2, minus 3 is negative 1. So this one won't work in this logarithm. I think it won't even work in this one. 1 minus 2, yeah, that's negative 1. So this 1 is extraneous. So that one is not going to work. This is our only answer. X equals 3. Those are all of our methods. Thanks for watching this video. I hope you skipped around and used it as you needed. Yeah. Have a good rest of your day. Remember all of these methods, they should all live in your head. Okay, bye-bye.